Welcome to this lecture on model fit in structural equation modeling. In this lecture today, we're going to talk about model fit indices and how to interpret them and report them in journals, and how to assess model fit in M+ output. So first, we need to cover a paradigm shift that you kind of have to undergo in order to move towards model fit indices and interpreting model fit. So there are two main schools of thought you can have in statistics. You have the classical school, which deals mainly with testing single hypotheses one at a time, and also it emphasizes explicit decision rules that everyone needs to follow. For the most part, this has been the school of thought that you have been taught in advanced statistics, and also in multivariate statistics, and probably any other statistics courses you've gotten. Now that you are in structural equation modeling, this moves to a different school of thought, the model school, which deals with evaluation of entire models. So you're evaluating a series of hypotheses simultaneously, and the rules become much less clear-cut and much more fuzzy. So many of you have probably heard me say, the graduate answer is it depends. We are now really in the it depends world. When we go through the model fit indices, it's really important to consider that these are general rules of thumb and not hard and fast rules like we do with p is less than 0.05 and with some of our impact factors and other things like that. We are dealing with modeling, and so we're going to be in a little bit more gray area as we move into this. A few other things about model fit before I get to the indices. When we have an over-identified model, so that's when we have positive degrees of freedom. That's what we want in our model because we have greater parsimony, so we have a more simplistic and a more parsimonious model that aligns much more closely to our hypotheses and is easier to explain. It tends to test our hypotheses more accurately because we don't have extra stuff in there. And if you remember from the lecture on estimation and identification, we run into this issue where we have to estimate them, and there's going to be error in that, and we want the error to be small as possible. But because there's that error, our model will not fit the data exactly. If we have a justified identified model, we will. And all of your fit indices will be perfect because it's an exact fit to the data. But in an over-identified model, there's going to be some misfit. And as that misfit gets greater, it can get to a point where we say, you know what, I just don't trust that this model accurately represents reality. And so the model fit indices are all about a way to test different parts and different pieces of that model to give us some information about how well it fits that data. Now, there are a lot of model fit indices, and different programs may give you different indices. We're going to go over the most common ones that are in M+, and the ones that are most commonly reported. But because there's a variety of them, a half a dozen or more of them that you tend to report, there's no single one thing that tells you that your model is good. And so we are going to use a variety of them. But because there's also many of them, you can run into a few problems when you're reporting them, trying to figure them out, and assessing those model fit indices. So number one, different journals and editors may have different preferences for specific model indices and even cutoff values for model fit indices. So, and not just journals and editors, but also reviewers. Some reviewers may request a specific model fit indice for a reason because it's common for them, or they believe it provides important information. So again, I'm going to show you the most common ones that are reported, but you'll occasionally see model fit indices differ from journal to journal, editor to editor, reviewer to reviewer. You may even see different reviewers of the same manuscript prefer different indices, different model fit indices. The last two are really about, so those first two problems are really external to you. So those are issues you'll see or problems you may come across in publishing your work. These last two are really problems that can come up for you as a researcher that you need to be aware of for yourself. Number one, because there's a variety of them, there's a possibility for confirmation bias. So you're only going to report and look at the model fit indices that are favorable to you. And if there's some that are unfavorable, you'll just kind of ignore those. You really need to look at them as a whole and not ignore pieces that are poor because it gives you important information that you may need to address in your model. The last one is you can become so preoccupied with overall model fit that you forget about the other important information, like how much impact does this model actually have? How big are your beta values? Does it even make sense? Do the parameter estimates make sense? Does the model make sense? So you don't want to get into an area where you are forgetting to see the bigger picture because you're so focused on model fit that you forget to look at your overall model and the parameter estimates and the impact factor of those to see whether this even makes sense and is meaningful. So, like I said before, there is no single model fit index that gives you all the information you need. You're going to look at a variety of different ones, about a half a dozen of them, and put them together to get an overall picture of your model. So some limitations that all model fit indices have. They're all going to have a variety of limitations. The fit indice, keep in mind, is only an average or overall fit of the model. So this gives you an overall picture of the model, but it doesn't tell you if specific pieces or paths of that model don't fit the data well. So there may be, while overall your model fits the data well, there might be portions of it that don't fit as well. Number two, because a single index reflects only a particular aspect of model fit, a favorable value of that index does not by itself indicate good fit. Again, you cannot use just one model fit indice to determine whether you have good model fit. You need to look at all of them together and see what kind of picture that gives you. Number four, values of fit indices suggest that adequate fit do not indicate that the predictive power of the model is also high. So just because you have good model fit does not mean that your model is actually impactful, that it has practical significance. So keep in mind that model fit is necessary but not sufficient to have meaningful, a meaningful model and meaningful results. Number five, the sampling distributions of many fit indices used in SEM are unknown, and interpretive guidelines suggested in this presentation for individual indices concerning good fit are just that, guidelines. So statisticians are constantly arguing about different model fit indices, where cutoff values are, or where cutoff, or what different values mean. And we want to make sure we don't get into that same piece with p-value where we really find these hard cutoff rules that we become a little bit too archaic in the way that we are evaluating model fit, where we want to be in the modeling school, not the classical school where we are dealing with fuzziness and grayness, and being willing to change and be open to those. With that being said, I am going to give you the generally agreed upon and most commonly agreed upon cutoff values that are often used. But it's important not to use them necessarily as strict cutoff values, but more so understanding what the values mean and where kind of the cliff starts to fall off, where once you get below or above a certain value, it really indicates a real significant problem in the model. All right, so these I'm going to go over the model fit indices. With each model fit indice, I'm going to describe what it is, what kind of biases it has, what are the generally agreed upon and accepted cutoff values, and then how to report it. So the first one is chi-square. So chi-square of goodness of fit. This one evaluates if the observed covariance matrix is consistent with a specified model. So essentially what it's doing is testing whether the null, it's testing the null is that the residual covariance matrix is 0. So remember when we talked about those three covariance matrices? The residual is the difference between the sample and the observed. So it's determining whether that residual covariance matrix is much greater than 0. If it's much greater than 0, then we will have a non-significant, if it's much greater than 0, then we will have a significant chi-square. We want the chi-square to be non-significant. If it's non-significant, that means it's the residual matrix is really close to 0. However, because we're dealing with chi-square and it has a p-value associated with it, it has a very strong bias where it is strongly biased by sample size. So your chi-square can very quickly and easily become significant due to sample size and not due to the difference for the residual covariance matrix being greatly different than 0. Generally, the cutoff value we want the chi-square to be non-significant, so p is greater than 0.05. However, because in SEM we tend to do a lot of large sample research, this one is very often significant. But the chi-square has another piece that's very important, and that's in doing model fit comparisons. So the chi-square goodness of fit, we are going to use this very often when we are comparing models, when we are constraining parameters to be equal to each other, or where we are comparing nested models. So we are removing some parameters and putting in more parsimony. Or sometimes if we want to decide to remove a few of our control variables that seem to not have an impact on the model, we'll do a chi-square difference test to see whether that we are able to do that. And at the end of this lecture, I'm going to show you how to do chi-square difference testing. And then I have in here how you report it. All right, the RMCA. So the RMCA is the root mean square error of approximation. This one assesses fit as a function of degrees of freedom. So what it's really doing is telling you how good of a fit there is depending on how many degrees of freedom on it. So this is really all about how complex is your model. If you have a super complex model, so in other words, fewer degrees of freedom, you're going to get punished by the RMCA. This one really likes you to have more parsimony. So the RMCA also has a confidence interval around it. So when you report it, you're going to report the RMCA value and its associated confidence interval. So RMCA equaling 0 is your best possible fit. So if you have a justified identified model, you will have a 0 for RMCA. Generally, what you'll see most people talk about is being less than 0.05 is best. That's where you want to be. You want to be less than 0.05. But really, between 0.05 and 0.08 is considered adequate fit. And then once you get over 0.08, some authors argue for 0.10. However, you'll see a lot talk about that RMCA should be combined with the CFI. And when combined with the CFI, you should really use that 0.08 cutoff for the RMCA. And there's a lot more consensus around this one than perhaps any of the other fit indices. That this one's a much more easy to follow, a hard and fast rule. So how you report it, you do the RMCA equals and then the RMCA value, and then you do the 90% confidence interval. So I have on the slide here on the bottom right how you would report that. The CFI is a comparative fit index. So what this one does is it tests your model, so the model that you are testing, the researcher's model, and tests whether it provides a better fit than the null model. So this is really a test to see whether your model fits better than the one that fits best with the research, or fits best with the data. So the main biases with this one is it's comparing it to a null model and technically comparing it to as bad as the model could possibly be. So it's going to take the null model, which is the most clear-cut model, versus the worst it could possibly be, and see it says, all right, is yours close to that worst as possible could be, or is it closer to the null model? So having a good CFI is probably the easiest of the fit indices to have look nice. If you have a bad CFI, you're usually in a pretty bad place with your fit indices and your model fit. It ranges from 0 to 1. 0 indicates that the model does not have improved model fit over the null, and a 1 indicates that it does. So the closer to 1, the better. Generally, we want this one to be greater than or equal to 0.95. I've seen articles where they have CFIs lower than 0.95, like the 0.85 to 0.90 range. Again, we're not doing hard and fast rules here, but generally, if you feel comfortable if your CFI is above 0.95. And we just report this one by saying CFI equals and inputting the value right there. The TLI is the Tucker-Lewis index, also known as the non-normed fit index. So the TLI it corrects for negative bias by taking into account the number or the degrees of freedom of the tested model and the null model. So it takes the degrees of freedom in the null model and then in your model, and then looks and compares those two. So the bias on this one is it tends to be unstable in studies with small or medium-sized samples. So you really need to have a large sample for this one to be pretty good and consistent. This one is similar to the CFI, where closer to 1 is what you want to be at with this one. And most people follow the general rule of like 0.95 or above is better, but that's much less agreed upon than the CFI. The SRMR is the standardized root mean square residual. So like its name indicates, this is all about the error or the residuals in the model. So this one is evaluated by calculating, or it's calculated by squaring the standardized residuals, summing them, and then dividing them by the number of residuals in your model, and taking the square root of the mean square residual. So what it's really doing is it's looking at all of those disturbances or errors in your model and looking at the average or overall error in your model. Now this one is biased. Its biases are that it's a biased estimator of population average residual indices because it is affected by sample size. So sample size can really affect this one. The cutoff value for this tends to be less than 0.10 is better. Being close to 0 is better for this one. And you just, like the CFI and TLI, it's just SRMR equals and then the value. And you want this to be under 0.10, and being closer to 0 is better. I have copied on here an example of what the output looks like in M+ for model fit information. You'll see at the top there the error, or the message that we all want to get. The model estimation terminated normally. And then under that, you'll see model fit information, and you'll see some indices that I didn't talk about because they're not commonly reported, like the log likelihood, the information criteria. You'll also see in there the chi-square test of model fit for the baseline model. We don't report that one generally, so you'll see the chi-square test of model fit. That's the chi-square that we test, and this one it's 1342.229, 159 degrees of freedom, and 0 p-value. So in this one, that p-value is not good for our model fit. However, I know in this one we have a very large sample size, and so I was not surprised to see that chi-square was significant. The RMCA here is 0.033, and again with the RMCA, we want that one to be closer to 0. And then we report the confidence interval. So there's the 90% confidence interval of 0.032 to 0.035. Generally on this one, we will report 3 decimal points out rather than the typical 2. And so we can feel pretty good. This RMCA looks good. And then we have the CFI and the TLIs. The CFI on this one is 0.94, so just below that 0.95 value. So I'd like it to be a little bit higher, but it's not a killer. And the TLI is 0.908, so 0.91 when we round to 2 decimals. And that one is not terrible, it's not fantastic, but it's adequate. I would feel comfortable with this one. And we have the SRMR there at the bottom, and that's 0.017. So that's below our threshold of 0.10 for the SRMR. So our SRMR looks great. Our RMCA looks great. Our chi-square doesn't look good, but then again, we have a huge sample, so unsurprising. And the CFI and TLI are okay. So overall, I'd say this model has an adequate fit. And how we would report that, let's pull this all together here. And when you put it all together, you will report your model fit indices in a single parentheses. And it's usually accompanied by a very simple, straightforward statement of the final model fit the data adequately. And we put them all together there, reporting the chi-square, the CFI, the TLA, the RMCA, and the SRMR. Order doesn't matter. Typically, people start with the chi-square, but order doesn't matter. And with semicolons between each of them, following the proper rules around how you report things within parentheses, just like you would with references, and having the confidence intervals in there as well. Now to wrap up today, or wrap up this first half of our lectures in this module, I'm going to talk about comparing models, so chi-square difference testing. Chi-square difference testing is pretty straightforward. You're going to be doing basic arithmetic. And this is a staple in SEM because we are constantly trying to have a more parsimonious model. And there's a lot that we do in SEM around constraining parameters to be equal to each other. So we do this a lot, and especially across autoregressive lag models, didactic modeling, as well as group comparison differences. Because one thing we do is constrain corresponding paths to be equal, and if the model gets significantly worse, then it means that they're unequal. If the model does not get significantly worse, then it means that those are equal. They are relatively the same, and that can, one, create a more parsimonious model, and two, really help us to give more contextualization to the results. So you'll do this a lot in constraining path, eliminating parameters, or even variables. Sometimes you're going to drop control variables that are non-significant in order to give your model more power and to make it more parsimonious. So the process for doing chi-square difference testing is pretty straightforward and pretty simple. Don't overcomplicate it. All you're going to do is take the chi-square of the more complicated model or the more complex model and subtract it from the more simple model. So you subtract the chi-square value to get a new chi-squared value, and then you subtract the degrees of freedom from each other, and then you just grab a chi-square calculator online that gives you a p-value and plug it in and see whether it's significant or not. If the difference test results in a chi-square that is significant, it means the model got significantly worse. And so we're going to reject that more parsimonious model because it got significantly worse. If your p-value is not significant, then the model is equivalent and we can accept the more parsimonious model. So if we're doing constraining paths, we can say those paths are equal to each other. If we're comparing a nested model, so a more reduced model with fewer variables or fewer parameters, we get not significant, we can use that more parsimonious model. If our chi-square is significant, we're going to reject that more parsimonious and stick with the original one. So let's look at an example here. Let's say in our main model, the model that we're testing, our chi-square equals 4.064 with 4 degrees of freedom. And then we constrain a few of the parameters to be equal to each other. And our new chi-square is 29.596, and our degrees of freedom are 24. We will then simply first subtract the chi-squares. So 29.596 minus 4.064, which gives us a chi-square difference of 25.532. And then we're going to subtract the degrees of freedom. So 24 minus 4, which gives us 20 degrees of freedom. So the chi-square difference is 25.532 with 20 degrees of freedom. You can then go online. This is the one I have here is just the first one that pops up for me on Google when I Google chi-square calculator. And you just simply put in 25.532 in the chi-square value and 20 in the degrees of freedom, hit calculate, and it will give you a p-value of 0.1818. So that is bigger than 0.05, which means it is not significant. So therefore, we can conclude that our models are equivalent, and therefore I can accept the more constrained model. And I have also right there exactly how you would report that. You do the chi-squared diff, that's chi-squared difference, is equal to 25.53, 20 degrees of freedom, and p-value equals 0.18. So the next half of this lecture coming up, we'll talk about how to actually run a model in SEM, and then how to interpret those results in the output.